Hey everyone and welcome. If you're gearing up for the LPIC-1 exam, you are in exactly the right place. Today, we're going to demystify Linux storage. We're going to take a deep dive and break down everything you need to know about taking a brand new disk from just a piece of hardware to a fully functioning part of your Linux system.
So, here's our game plan. We're going to follow the entire journey of a storage device, right from the beginning. We'll kick things off with the absolute basics of disks and file systems. Then we'll check out the tools of the trade, figure out how to actually make that space usable, and then we'll wrap up by touching on some of the more advanced and modern storage tech you'll run into.
Okay, let's dive right in. So, picture this. You just got a shiny new hard drive. You've plugged it in, it's physically connected, but your Linux system has no idea what to do with it. Let's walk through how we bring that drive to life.
Right now, that new drive is basically just an empty box. It's a physical container that can hold data, but it's a completely blank slate. Before we can even think about saving a single file, we have to give it some kind of structure.
And that structure is called a file system. The best way to think about it is like a digital filing cabinet. It sets all the rules for how our files and directories are going to be organized, how they're named, and how we find them later. Without a file system, all your data would just be a chaotic, unusable mess of ones and zeros.
And this slide right here, this is a core concept for the exam, so really let it sink in. It shows the 4 crucial steps to make a disk usable. First, you've got the physical disk itself, the hardware. Then you slice it up into logical sections called partitions. Inside each of those partitions, you create a file system. And finally, you attach that file system to a directory on your system, which we call a mount point. It's a simple hierarchy, but it's absolutely fundamental.
So how do we actually, draw those lines on our disk to create partitions? Well, let's take a look at the essential command line tools you'll be using and the special codes that tell Linux what each partition is for.
You're going to run into 2 main tools for this job. For older systems that use what's called a master boot record, or MBR, you'll use fdisk. Now, MBR had some serious limits. It couldn't handle disks bigger than 2 terabytes. That's why on pretty much any modern system, you'll be using gdisk, which is made for the newer, much more flexible GUID partition table, or GPT. The good news? They work almost identically, so if you learn one, you pretty much know the other.
But if you want the real Swiss Army knife of partitioning, you need to know about GNU Parted. This tool is a powerhouse. It can handle both MBR and GPT disks, no problem. And its killer feature? It can actually resize partitions, which is something fdisk and gdisk just can't do. It's an incredibly useful utility to have in your back pocket.
Okay, pay attention here, because these codes are super important. When you create a partition, you have to assign it a type code that tells the operating system what it's for. For the LPIC-1 exam, you absolutely positively have to know code 83 for a standard Linux file system and 82 for swap space. The other two, 8E and FD, are for more advanced things like LVM and RAID, which we'll get to in just a minute.
All right, so our partitions are defined. Now what? Let's see how we actually make them able to store files and support our system. This is where we get into formatting and setting up our virtual memory, or swap. So, once you have a partition, you have to format it with a file system. And the command for that is mkfs, which is just short for make file system. So if you want to use the really popular ext4 file system on your partition, dev/sdb1, the command is just mkfs.ext4 dev/sdb1. It's the same idea for other file systems too, like XFS, which you see a lot on servers.
So why would you use a file system like ext4? Well, one of its most critical features is called journaling. You can think of a journal as a to-do list for the hard drive. It tracks changes that are about to be made. So if your system suddenly crashes, the next time it boots up, Linux can look at that log file to fix any inconsistencies and recover your data. It's an absolute lifesaver.
All right, next up, swap. The easiest way to think about swap space is as an emergency overflow for your computer's memory. When your physical RAM starts to get full, the operating system can take the least used bits of data from RAM and move them over to the swap partition on your disk. This frees up your fast RAM for the stuff that's actively running.
And setting up swap is a super simple 2-step process. First, you run the mkswap command on your swap partition. This just prepares it and writes a special signature. Then you run swap on to activate it and tell the system, hey, you can start using the space now. That's it.
So we've got our basic partitions set up. But what happens in the real world? What if a critical partition starts to run out of space? Or worse, what if a whole disk just dies? Basic static partitions aren't going to cut it for those kinds of problems. And that's where we need more powerful tools like LVM and RAID.
LVM, or Logical Volume Management, is basically a sysadmin's best friend. Think of it like this. Imagine your disks are a bunch of small water bottles. LVM lets you pour all that water into one giant flexible tank. From that big pool of storage, you can then create logical volumes of any size you need. And the best part? You can easily add more bottles to the tank later or resize your volumes on the fly. It's all about flexibility.
Now, RAID, on the other hand, is all about teamwork. It's a way to combine multiple physical disks so they act as a single unit. You do this for one of two reasons, either to get a major speed boost or, and this is often more important, to create a safety net for your data in case a drive fails.
For the LPIC-1 exam, you really just need to know the basics of the first two levels. RAID 0 is called striping, and it's all about speed. It writes bits of your data across multiple disks at the same time. But it's risky. If one disk fails, you lose everything. Then there's RAID 1, which is mirroring. This is all about safety. It writes the exact same data to two or more disks. It's a bit slower, but if one disk dies, no big deal. Your data is still safe on the other one.
Okay, let's wrap this up by looking at two modern technologies you are definitely going to run into on newer systems: the BTRFS file system and the UEFI boot process.
BTRFS, which a lot of people just call ButterFS, is a really cool next-generation file system. It's packed with advanced features. For starters, it has LVM and RAID-like capabilities built right in. It can also automatically compress your files in the background to save space, and it uses this really cool concept called subvolumes, which lets you treat directories almost like they're their own separate partitions.
Now, switching over to the hardware side of things for a second, you'll find that pretty much any computer made in the last decade or so doesn't use the old-school BIOS to start up anymore. Instead, they use UEFI, the Unified Extensible Firmware Interface. It's just a much more modern, secure, and flexible way to get the hardware ready and hand off control to the operating system. The number one thing you need to remember about UEFI for the exam is that it requires its own special little partition. It's called the EFI System Partition, or ESP for short. This is where all the bootloaders and other critical files needed to start the OS live, and in the Linux world, you'll almost always find it mounted at /boot/EFI.
And there we have it. We've gone all the way from a completely blank disk to a fully functional storage system, hitting partitions, file systems, and even advanced tools like LVM and RAID. So that leaves us with one final thought to chew on. Now that you know all the building blocks, how would you set up the storage for a web server where data safety is critical versus how you'd set up your personal laptop, where you might want more flexibility? Thinking through these real-world scenarios is really the key to mastering these